Okay, Tejas, you have any specific questions to ask? Okay, hi Neetu Srivastava. If you have any questions, you can shoot. Neetu, are you there? Hello, Neetu. Hello, guys. You have any questions to ask? Please ask. Sairam? Hello. I can't hear you, Sairam. You're mute. Okay. I have some specific questions to solve. Can you guys see my screen? Sairam or Neetu? Okay. Hey, Bunty. Bunty, can you hear me? Okay, all right. So I'm solving these problems, okay? Your problems, whatever you asked for. So let's see. Okay, so this is the first question that you asked for. So the following binary values are applied to the x and y inputs of the NAND latch shown in the figure in the sequence x equal to 0, y equal to 1, x equal to 0, y equal to 0, x equal to 1, y equal to 1, right? So if this is x equal to 0 and y equal to 1, so we know the NAND operation, right? AB. This is A dot B complement, right? If one of them is 0, then obviously 0 complement that will become 1, right? So if one of the input is 0, the output will automatically will become 1, irrespective of other input, right? This one is applied here. Now what is this? 1 and 1 complement, that is equal to 0, right? So for the first combination, P equal to 1, Q equal to 0, right? Then erase this, okay? Just erasing. Then x 0, P is already 1, Q is 0, then x 0, y 0. So according to the logic, the output will become 1, Q also will become 1, right? So P equal to 1, Q equal to 1. This is also fine, right? Next logic. So P1, Q1, right? Then what is our input that apply? X equal to 1, y equal to 1. Now the inputs are also 1 here, right? Now AND gate, both the inputs are 1, output is nothing but 1 and 1 whole complement, that is equal to 0. Now which one will become 0 first? Whether this one will become 0, let's say, assume that this output will become 0 first. Then this 0 will be applied here. Then 1 and 0 whole complement is 1. So P equal to 0, Q equal to 1 is one possibility. Otherwise, instead, if these are already 0, 1, 1, right? Okay. So instead, if this process is fast and this becomes 0, then this 0 is applied here, this will be 1. So first combination pakka P equal to 1, Q equal to 0. Second combination also pakka P equal to 1, Q equal to 1. For third combination x equal to 1 and y equal to 1, there is an ambiguity, right? It can be P equal to 0, Q equal to 1, or it can be P equal to 1, Q equal to 0, anything that depends on how fast either NAND gate 1 or NAND gate 2 process it faster, right? So we are not sure because those are not given. So we choose these two options also, right? So P equal to 1, Q equal to 0, P equal to 1, then P equal to 1, Q equal to 1. Okay, these options, right? Option C and D are somewhat relating. Then P equal to 1, Q equal to 0 is there, P equal to 0, Q equal to 1. Okay, option C is right answer. Okay, Bunty, are you clear? Right. So anyone has any question here? Okay. Hey, are you guys attending any previous class or what? Oh, okay. Okay, all right. Thanks. No problem. So, okay, fine. Then next, this one. For the circuit shown in the figure, D has a transition from 0 to 1 after, right? From 0 to 1 after clock changes from 1 to 0. Assume gate delays to be negligible. Which of the following is true? Okay, right? You need to know what is the value of Q. Okay, so let's do that. So let me draw this clock as it is what they gave. This is the clock, right? So this is 1, This is 0. And what is D? You see this, there is a lag, some lag is there here in this, right? So initially it was 0. Then after some time D has become 1. Okay. So now we need to find what is Q, right? So initially what is the value of D? D value is 0, right? Let's say I am calculating at this time interval T1, okay? Okay, before applying the clock edge, right? So let's say this initial value is 0. Hmm? This is 0. This is a NAND gate, right? This will become 1. Okay, these are NOR gates, right? These are NOR, NOR, NOR. This is NAND. Hmm? This 0 is applied here. Then, but at this point, when D is 0, clock is also 1, right? So this one is applied here. This one will be applied here. That's simple, right? So 0 plus 1 whole complement. 0 plus 1 whole complement is 0, right? 1 plus 1 whole complement is also 0. Now what is this actually? Just RS latch, right? Basic RS latch. For that, whatever is Q, that will, like, see, this is R equal to 0, S equal to 0 condition, okay? R equal to 0, S equal to 0. What happens with R equal to 0, S equal to 0? Present state will be repeated, right? Next state is equal to present state. That's all. But what is the value of Q presently? Did they mention anywhere in the question? You see, nowhere it is mentioned. So let's assume it has a Q only, right? So we don't know what is the logic value here. So let's assume like that. Okay, it's Q only. Something, whether it can be 0 or 1, right? Now, now clock changes here, right? From 1 to 0 here at this point, right? At this transition. Here, what is the value of D? 0. Clock also has become 0, right? So let me interchange the values. Let me change the values. So let it be like this. And this we know already. Just removing it. Now what is our value? Clock value 0. Let me use some other color. Now clock has also become 0. Where at time instant T2. Hmm? Clock equal to 0. D is still 0. Okay, see, D is becoming 0 to 1 after some time. Hmm? So D value is 0. Clock value is 0. This is the clock. Since D value is 0, this is going to be 1, right? This is 1. 0 plus 0 whole complement is 1. 0 plus 1 whole complement is 0, right? Now you know, right? Let me remove this, right? R gate, NOR gate, right? NOR gate, A, B. This is A plus B whole complement. Let's say if A is 1 or B is 1, 1 plus B or A plus 1. It doesn't matter. This is 1, this is 1. 1 complement is 0, right? If one of the input is 1, output is going to be 0. So you don't need to worry about this input. This will become 0. Then this 0 will be applied here. Then 0 plus 0 whole complement is 1. Are you getting it? So Q at this point has become 1, right? So I don't care really what exactly the previous value is. Let's assume that's something like Q, whatever it is. It's not 0 or it's not 1, right? Now, that's not the end of it, right? There is one more change here. All right, see here. At time interval T3, right? Till that point, Q will become 1, right? Now here, D has become 1, right? Now there's a new value on D. Hmm? Let me erase all these things. This is 0 and 1 will be there. Q and Q bar. Okay, only there is a change on D, right? So now let me change another color, right? This one. Now D has become 1. Since D has become 1, right, this is 0. Hmm? So D is 1, clock is 0, this 0 is here. So 1 plus 0 whole complement is 0, 0 plus 0 whole complement is 1, right? So because of this, right, because of this 1, this will become 0, this 0 will be applied here, 0 plus 0 whole complement is going to be 1. So here the Q will fall back to 0, right? So what will be the right answer? Q goes to 1 at the clock transition and close to 0 when D goes to 1, right? So option C could be the right answer. Bunty, are you clear, boss? No confusion, right? Very clear. All right. Now, next question. What is that they're saying is this, right? So, the digital logic shown in the figure satisfies the given state diagram when Q1 is connected to the input A, right, of the XOR gate. Suppose XOR gate is replaced by a XNOR gate, okay? Suppose which one of the following operation preserves the state diagram? Means there is no change in the functionality, right? So A is Q1, right? This is Q1. Now, what has changed in this circuit? Except this, nothing else has changed, right? Instead of XR, this is Q1, there is going to be XNOR, right? That's what the statement, right? XR gate is replaced by a XNOR gate, right? This is going to be S, right? Which one of the following option preserves the state diagram? Means there is no change. That means that let's say this is something called K. Let's say this is K. Now this is M. Your M should be equal to K. That's all. Whatever is the output. If that is again is a K, then there is no change. Literally, right? Even though you replace with X XNOR, if M is equal to K, then your state diagram will be preserved. You guys understood the logic? Let me know yes or no in your chat box. Okay. All right. So, where this A should be connected? Now, you know the XNOR and XOR gate, right? See, for example, I have a XOR gate, right? It is AB, let's say. What is this value? A complement B plus AB complement, right? Now, I want let's say XNOR gate is there. What is this actually? A complement B complement plus AB, right? Now, I want XNOR also to act as XOR. What I should do? Instead of applying A, you apply A complement. What will happen? A complement. Instead of A complement you are applying, right? So what will happen? What is this? Just invert A and give it. That's it. You will get the same thing, right? This is, let's say, M. Let's say this is K. Now what is that you are supposed to give? Instead of giving Q1, you give Q1 complement. Then these outputs will be same. Correct. So what is the right answer? Input Q1. Oh, sorry. Input A is connected to Q1 complement. Bunty, clear? Because you posted these questions, right? That's why I'm asking you more to respond. All right. Okay. Anybody has any questions so far? Next question. Okay. Can you guys try this? I'll just give you 2 minutes. Try. Okay. Any answers? Let me know in your chat box. So, what you need to do is, okay, can you guys hear me? Right. Now you see how, you see, let's say you write present state, next state, right? Okay. So, what are the inputs, right? What are the inputs you need to apply to move from present state to X state, okay? So, what are the outputs with the state outputs A, B, C, right? And binary inputs X, Y, and Z, right? X, Y, and Z. So here if you see, you go from A to A, okay? So let's say you move from present state to A. Means Y equal to 0. What does it mean? What about X and Z? Y equal to 1 they are saying. What about X and Z? It can be anything, right? Don't care. That means what? 0, 0, 0, 1, 1, 0, 1, 1. That means Y will be always 1, but this can be anything. Like, so any of the combination, okay, 4 of this combination, I am writing here together 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1. All these combinations can take you to A to A. Next, where else? A to B. To move, let's say you are at present state A. Let's talk one by one node by another node, right? X0, Y0, Z0, right? So 0, 0, 0. Clear, right? Now again there is something called A to A. See this node. What is that saying? X0, Z1, right? What about value of Y? Don't care. That means 0, 0, 1 can be one combination, 0, 1, 0 can be another combination, right? So A to A again, one more combination is there, 0, 0, 1, 0, 1, 0. This combination also will take you to A to E. Right. So it's like these two are the same, right? These two you can combine. Those two sets will take you from A to E because present state and next state are same. Next, what is another one? A to C. You see A to C. A, C. Present state is A. You want to move to C. What are the inputs that you should apply? X1, Y0, Z is not given. Don't care. So 1 0 0 1 0 1. See, if you take 1 0 0 and 1 0 1. Are you clear? 1 0 0 and 1 0 1 will make you to A to C. Right? Similarly, can you try for B and C? Is there any conflict in this? Can you check, cross check once? In these combinations, is there any conflict in that? When I say conflict, right? Let's say there is, let's say one combination 0 1 0. You take this combination. You are going from A to A. Now, by any chance, if that combination says that when you apply 1 0 1 0, you go to A C, then this is called conflict. Means one way you are saying move from A to A, another way you are saying A to C, then this is called conflict. Right? Then that is called as ambiguously defined. Right? So here you see these combinations 0 1 0, 0 1 1, 1 0 1 1 0, 1 1 1 A to A. Then move from A to B, 0 0 0 A to B. Then 0 0 1, 0 1 0 again A to A. Then 1 0 0, 1 0 1. Is there any ambiguity in this? Then you can say that transition from state A are ambiguously defined. Right? You try similarly for B. You try similarly for C. If you find there is an ambiguity, then that option will be the right answer. Okay, so you just try to, you see, it will take some time taking. We have some 3 more questions to solve. So try on this and then see which option can be satisfying. Right? So let's move on to the next one. This one. A finite state machine is implemented using D flip-flop, A and B, and logic gates are shown in the figure. The 4 possible states of the FSM are 0 0 0 1 1 0 1 1. Assume that Xin is held at a constant logic throughout the operation of the FSM, finite state machine. When FSM is initialized to QA QB 0 0 and clock after few clock cycles, it starts cycling through. Okay, it's also a similar one. So what you need to do is you have something called input, right? And you have see this combination is QA QB, right? Hmm? Now I am concerned about next state. Okay, when I say QAN, what I mean to say is this is next state. When I say QA, this is present state, right? QAN, see this in this A flip flop depends on D, right? QAN is nothing but D, right? What is D depends on? Is XOR combination of QA and QB, right? So means to get QA XOR of QB. QAN is just QA XOR of. What about QBN? Depends on this guy, right? What is this guy? QA and X in complement. This is NAND operation, right? NAND. This is QA and X in complementation. Now what you need to do is you first take x in as 0. Let's say 0, right? So before taking 0, for example, how you need to do is this, right, this way. Okay. When nothing is applied, 0, 0, then you take x in equal to 0. Because QA and QB are 0, 0, this is 0 XOR of 0, right? Right? This is 0 XOR of 0 will be 0, 0 and 0 complement is 1, right? Because QA is 0, right? Then X in is 0. Now once you apply the clock, what will happen? These values will be there, 0, 1. All right? Now, before applying next clock pulse, you need to calculate what are these values are. So before you apply clock pulse, what are these values? Now QA is 0, Q1 is 1, QB is 1. So this is 0 XOR of 1, that is 1. This is 0 and 1, I mean, sorry, QA is 0 anyways. Xin is 0, Xin is 0, complement, that is equal to 1. So both are 1, 1 right now. So when you apply clock pulse, right, so both will be 1, 1. You continue and then see if there is any cycle that will be repeating or not. Now, the present states are 1 and 1, right? Accordingly, these inputs will change. Now, 1 XOR of 1 is 0. What is this? 1 and see, Xin is always 0. So, it is always 1. QBN will always be 1, right? So, you have 1 and you have 0 when you apply the clock, right? Similarly, okay, you guys try for, Xin equal to 1. So, this is 1, this is 1. So, you will get 1, 1 when you apply the clock. Again, the same thing, right? See this 0, 1 to 1, 1, it has become 1, 1 to 0, 1. Then again 1, 1. Obviously, again 0, 1 will come. Correct? So, when Xin is equal to 0, how many states that are repeating? 0, 1, 1, 1, right? 0, 1, and again 1, 1. This keeps on repeating, right? So, what I can say is when Xin equal to 0, two states. Okay. So, I can say that only 2 of the 4 possible states if Xin equal to 0. Can you guys try for Xin equal to 1? Okay. So, let me try this also here. Ls. Focus on the process, not the answer. Finally, anyways, if process is right, if you are not doing any mistake, QAN, QBN, as I said, this depends on QA XOR of QB. This depends on QA and X in complement. Initial values are 0, 0. Nothing is applied. Now compute what will happen. So 0, 0 means this is going to be 0. And of course, now X in is 1. So QA is 0. This is 1. Complement, that is equal to 1. Are you getting it? So you will get 0, 1. Next, before you apply the clock pulse, compute these values. Right? This is after application of the clock pulse. So before you apply the clock pulse, this is 1, this is 1, right? Because QA XOR of QB is 0 XOR of 1, 1. And this is 0 and 1 whole complement is 1, right? So when you apply the clock pulse, your X in is 1 and this is 1, 1, right? Next. 1, 1, right? So 1 XOR of 1 is 0, 1 dot 1 whole complement is 0. You see that? 1 XOR of 1 is 0, 1 dot 1 whole complement is also, 1 and 1 is whole complement is also 0. So when you apply the clock pulse, when X is 1, you will get 0, 0. Now, 0, 0 means again you will get same story, right? So when X in is 1 means 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1 means 3 states are repeating, right? When X in equal to 1. So if I take X in equal to 0, 2 states are repeating. If I take X in equal to 1, 3 states are repeating. So I choose the right answer accordingly. All of the 4 possible states X in equal to 1. No. Then only 2. Okay, first let me strike out what is not answer. All of the 4 possible states, no. 3 of the 4 possible states if X in equal to 0, because X in equal to 0, 2 states only, right? Then only 2 of the 4 possible states X in equal to 1. X in equal to 1, 3 states, right? No. Only 2 of the 4 possible states if X in equal to 0. Yes, that's the right answer. Option D. Hey, are you guys clear with this? Say yes or no through your chat box, please. Bunty, what happened? What is the issue? Come on, tell me. No, no. What is your question? Okay, for X in equal to 1. Now, which combination? For 0, 1, you are saying. Should I repeat it here? Okay, fine. So let's say QA XR of QB is 1, right? Bunty, please, communication, please. What is this one? Tell me, what is this value? Tell me. Ah, ah, what is this? 1. So when you apply clock pulse, what will happen? 1 and 1 will be there, right? Next. Now you tell me, Bunty, what is sorry, what is this value now for the next phase? QA XR of QB is 0, Bunty. 1 XR of 1 is what? That's what I'm saying. 0 only, na? What is this one? So when you apply clock pulse, what will happen? 0, 0 will be passed to the outputs, right? Yes or no? Doubtful? Okay. So now what will happen? Again, same cycle will repeat, right? You computed already. When 0, 0 is there, then what will happen? 0, 1 will be there, then 1, 1, then 0, 0, right? I'm saying when you take x in equal to 1, 3 states will be repeated. When you take x in equal to 1, 0, 2 states will be repeated. Now accordingly choose the answer, whichever is the right answer. All right, Bunty? Oh, all right. Okay, guys. Can anyone try this problem? It's fairly very simple actually. Simple logic is there. There is finite state machine. For that, there is an input only clock, right? See, this is. So green to yellow, yellow to red, red to green. In each cycle, green is turned on for 30, 70 seconds. Yellow is turned on for 5 seconds. Red is turned on for 75 seconds. So the traffic light has to be implemented using a finite state machine concept. The only input to this FSM is a clock input, right? Only the clock input with a 5 cycles time period. The minimum number of flip-flops required to implement. See, think like a hypothetical situation, right? Now let's say there is A, there is B, there is C, right? A to B, B to C, and C to A. Again, let's say for example this cycle. To move from A to B, only input is clock. Hmm? Right? This is the time period, right? 5 seconds. Means to move from A to B, not necessarily all the time you can move from A to B. You can move from A to A also. Right? After 5 seconds, this is a clock. Okay, this is a clock. This is a clock. When you apply the clock pulse, you can stay either in A, or you can move to A, or you can move to B, or you can stay again back in A after 5 seconds. That's what I'm saying. Are you getting it? Right. So the point here is how many flip flops are required to implement this FSM. If you look at it, let's say for example, 75 plus 75, right? 70 seconds. Total time period that you require is 5 seconds plus 75 seconds. Okay. This is around 150 seconds, right? And for every 5 seconds, you need to change the state. I mean, you will come back to the same state, right? But you need to change the output. Let's say, for example, if that is required, you can change it, otherwise, no problem, right? So, how many flip flops are generally required is just say, for example, 5 seconds divided by 5. If you do, like, you need to change 30 states, right? So, to implement 30 states, how many flip flops are required? 5 flip flops, right? Okay, this one next. In the circuit shown below, A positive edge triggered D flip flop, right? A positive edge triggered D flip flop, sensitive to that positive edge. That's what it means, right? Is used for sampling the input data D in using a clock, right? So the XR gate output is 3.3 volts for logic high and 0 for logic low, for example. The data bit and clock time periods are equal, and the value of delta t by t is 0.515, where the parameters are shown in the figure. Assume that flip-flops and XOR gates are ideal. If the probability of the input data bit transition in each clock period is 0.3, that means that uh, whether the d in can change or not. Okay, that means if this is 0, to change 1, the probability is 0.3. Or if the input is 1, to change to 0, the probability is 0.3. Are you getting it? Right? So it's a simple, similar problem that we need to look at it. Okay. Now D in. Now let's say D in, we assume D in equal to 0 first, then we will move on, right? So this is the sensitive area here. D in, okay, D in. You see here, after delta T, there is a probability to change, correct? So let's say there is 0.3% 0.3 probability, and then d in has become 1. Okay, then it will move on like that, right? Now you consider one cycle, because they are talking about average value of the input voltage at the node x. So what is x here? If you look at it, x is, you see this, x is d in xr of q. So what is q actually? Is just d in, right? Here till this point, right? So let's assume that because d in is 0, let's assume 0. At, at t equal to 0 at this point, right? So let me change the color. I think it is very messy right now. I understand that. Q is 0. Now here again d is 0. So d will 0 and d continues to be 0 until next clock pulse comes. All right. So now I think I made it little messy here. Okay. So let me try to now that the basics are clear, let me erase all the ink on this. Okay. I think I'll cut this guy. Let me put it like this. This is easy. So let me draw this once again. The clock. There is a clock here. And it is edge sensitive, right? Positive edge sensitive, right? Then D in. You see, I'm assuming the initial values are 0. You see, there is a lag of delta t, right? I'm just continuing the same thing. There is a lag of delta t with a probability p equal to 0.3, it may change to 1, right? Hmm? Then it will continue. Don't worry about after this, because one cycle you need to concentrate. Then Q is equal to D in, right? When clock pulse is positive, only at this area. So let me draw Q is 0. Since D in is also 0 here, same 0 will continue. Here it may become 1, but it's okay, doesn't matter because our focus is here, right? Your focus is on the one cycle because average. So focus on one cycle. We can calculate. Then what is that average value of x they are asking, right? What is x? Q XOR of dn, right? This is Q, this is dn, right? XOR of dn. So x, this is 0, this is 0 means this is 0 here. And here 0, 0 means till delta t time. We don't know what exactly is delta t right now. Let's see that later on. Then from here, this is 0, this is 1. That means that your output will be 1. Right. Now, they also clearly told logic 1 represents 3.3 volt, right? That's what, right? 3.3 volt. Then logic 0 represents 0 volt, correct? I think, yes. And 0 volt for logic 0. So, what is the average of x? We know average value, right? X average. We know that, no? Integral 1 over t, 0 to t, x of t dt, right? You find the entire area divided by the time, correct? So here what is this? 0 into delta t, this is 0 volt plus 3.3 volt into what is this one? What is this value? This is total time period, right? Between one clock to another clock, right? This is t minus delta t. But the main point here is this, okay? There is a probability here. If you are considering 1 means with a probability of zero point 0.3. So you just multiply this with a 0.3. When only there is a 30% chance that this has become like that. Otherwise, it's fine. What is the total? T. So this is 3.3 into 3.3 into t minus delta t by t. Right? So this is 0.3, 3.3, 1 minus delta t by t. Okay, this is delta t by t is 0.15. Correct? That's what they have given already, right? See here, delta t by t is 0.15. So this is zero point 0.3, 3.3 into 0.85. How much is this? Whatever is the answer accordingly. Now, people may ask, sir, what if we start with the d? We assume that d in equal to 0. What if I start with d in equal to 1? You will end up getting the same thing. Okay, try that also. No problem. Okay, so the answer is going to be the same. Okay, Bunty, are you clear? Don't other people don't think that why I'm calling Bunty all the time. The thing is, he has asked me to explain all these questions last week. So if you have any questions, you can mail it to me or you can ask me right now. You can just solve it. Okay. By the way, what is answer to this one? What is the final answer? X average. Okay, Bunty, what's the answer? Okay. What if you take d in equal to 1 initially? Shall we try that also? Okay, let us try that. Hmm. So this is clock, right? And d in. So instead of assuming a 0 initially. Now I'll assume a 1, right? Then there is something called delta t time. Here I'll assume that same probability 0.3 times it will fall. Something like that. Means this is the probability with which we change, right? So if you assume from 0 to 1, then assume from 1 to 0. So then what will happen to Q? Accordingly, let's say whatever is the value earlier, doesn't matter whether it is 0 or 1. At this point, D is equal to 1, so Q will be 1. And then continue. Right? You focus on one cycle, right? X. What is the value of X? So here it doesn't matter. I am concerned only about this. So between 0 to delta t, so Q is 1, D is also 1, so output will be 0. From delta t to this is in this t minus delta t time, here it is 0, I mean, sorry, it is 1, this is 0, so obviously it is going to be 1, right? You see that waveform and this waveform, same, right? 0, 1. Here, 0 and 1. And there is a probability also, p equal to 0.3, right? So the x average, if you find out, again still it will also give the same thing. All right. Okay, I'll stop it right now. If you have any questions, you can ask me. Otherwise, we're good to go. I'll just wait for 1 more minute. If nobody asks questions, you can leave. No problem. Yeah. Hmm. Okay then. Bye bye. See you guys.